Hello again, Physics 30s. In today's lecture, we are going to continue to talk about the refraction of light, although this time around we're going to apply it to how light behaves when it interacts with a thin optical lens. Learning outcome for today is to describe both qualitatively and quantitatively simple optical systems consisting of only one component for both lenses and curved mirrors. I have a couple of illustrations of the different kinds of lenses we're going to discuss today, one being a convex lens and another one being a concave lens. And we'll go through more of the details as to what separates these in a moment. First thing I want to point out here is that when light hits a lens, there are actually two different sets of refractions that occur. As the light enters the lens, it's going to slow down. You're moving into an optically less dense medium. And we can see this from the illustration. So I have a ray of light approaching in a parallel direction to like a horizontal plane. And then this dashed line represents the normal line. When you go from one medium into another one, the speed is going to decrease. And that's illustrated by the fact that if we actually extended this ray out to show what would happen if there was no refraction, and ask ourselves, well, what happens to this ray of light with respect to the normal line? It gets closer to the normal line. If a ray of light bends towards the normal line, that's an indication that it does slow down, and that's what happens when you would pass from air into glass. There's also a second refraction when the light attempts to exit. So as the light tries to exit this lens, and again, let's draw another line just to show the direction of the ray of light if there was no medium change, which would look like this. And then what's happening to the ray of light with respect to my dotted normal line? Well, it's getting further away from it. If the normal line is getting, if the ray of light is getting away from the normal line, that's an indication that the ray of light is speeding up. One other thing to note here is that you can kind of model the lenses using two different spheres. So this is going to be a little bit different compared to like looking at a spherical mirror. So let me show you what this would look like. So let's take this side, and we're going to try to draw like a sphere or a circle shape to it. So if I did that, maybe it looks something like this. In the direct center, we'd have our center of curvature. Halfway between the center of curvature and this side of the lens, we would have our focal point. That's one circle. If I draw another one, so let's use the other side of the lens, we could draw a second circle. Obviously, it doesn't look as good as the first one. And I might have a center of curvature that's right here. And the focal point of the center one would be located halfway between the center of curvature and the edge of the lens. So one thing that's going to make this a little bit different compared to spherical mirrors is we're actually going to have two different focal points and two different center of curvatures that we need to consider. Types of lenses. They're already shown on the previous two slides, but let's give more of a definition as to how these lenses work. Starting with a converging lens. A converging or a convex lens is one where you have light rays refract. Again, refract means we pass through a material, and when we pass through, there's a speed change, direction change, and a wavelength change as well. And they converge towards a real focal point. This is something else that's different in comparison to the mirrors. For a mirror, the light would hit the mirror and then bounce back. So we call the left-hand side the real side, and we call the right-hand side the virtual side. For a lens, though, refraction's occurring, the ray of light actually passes through. It goes to the other side. So it turns out we're going to swap sides in terms of what we identify to be the virtual side and what we identify to be the real side. Therefore, we're going to call the opposite side now the real side, and we're going to call the side where we're going to have our object on the virtual side. That doesn't mean your object's virtual. It just means if we form an image, the image can only be seen if you look through the actual lens. As where if we can form an image on the real side, we could actually project it onto a screen. Here's a good example of this. This convex lens is a lens that you actually have in your eye. And what it does is it takes rays of light and it focuses it towards a focal point. And I believe if you have like really good vision, this should be perfectly focused on your retina. If it's not perfectly focused on your retina, then you can wear glasses that perform some kind of correction so that you can get all the rays of light focused on the retina. But that's one example. Like your eyeball does have a convex lens, and it does cause rays of light to converge towards a real focal point. The screen would be the retina, which is taking those light rays and sending some kind of like transmission to your brain through the optic nerve in terms of how to perceive the image. We also have a diverging lens or a concave lens. A diverging lens is one where rays of light diverge as if they are coming from a virtual focal point. So for a converging lens or convex lens, the rays come together at a focal point. For a diverging lens, the rays spread apart, they divide, they diverge, as if they originated from the virtual focal point. And by the way, if you're wondering why one is concave and one is convex, again, concave means you're striking like the inside of like the sphere, and then convex means you're striking the outside of it. So things are a little bit reversed here and compared to a mirror. For spherical mirrors, your converging mirror was concave and your diverging mirror was convex. But for lenses, your converging lens is convex and your diverging lens is concave. There should be a difference though, because mirrors and lenses work completely different. Mirrors reflect light and lenses refract light. Just like with the mirrors, we are interested in how we can use the mirrors to form an image. Now, technically speaking, the way you would need to predict, well, how do you draw one of these rays, is as follows. First of all, what you'd have to do is identify, okay, where does my ray of light hit the surface? Then I need a tangent line to represent the surface. Okay, so a tangent line might be this line here. Then you'd have to draw a normal line. Then you would have to measure the angle of incidence with a protractor, theta 1, and then use the law of refraction. You can use the law of refraction to get the angle of refraction. So the angle of refraction would be this one, theta 2. Take a protractor out after you've calculated it, and then you can figure out how that ray refracts. Then you do some geometry inside the lens, and you can figure out what theta 3 is. Then once again, you'd have to draw a tangent line at the surface, draw a normal line to that, apply the law of refraction again, and then you could get the angle of refraction. You could finally draw that refracted ray. That's way too much work. And it involves too much error as well, because once again, you're drawing tangent lines. So just like with the mirrors, we're going to have 3 rules that we can use to efficiently construct our images or efficiently construct ray diagrams. So here are the rules. Rule 1. An instant ray that is parallel to the principal axis will refract through or away from the real or virtual focal point. The information I put in brackets is going to be applied to a diverging or a concave lens, as for the information that's not in the brackets applies to a convex one. Well, let's look at a picture for this. Okay, so an instant ray of light that is parallel to the principal axis is going to refract through the real, this one's the real focal point, through a real focal point. And what we do is we only show the ray of light bending once. We draw a vertical line through the center of the lens, and then we just draw the ray to the center. And then when it hits the center, that's where we start to change the direction of the ray. Again, if you wanted to, you could confirm that it does this by applying like that complex procedure I just described with tangent lines and whatnot. However, all we need to do is just memorize these rules and then use them efficiently to construct the ray diagrams and form the images. Now, that's for a converging lens. For a diverging lens, if you have a ray of light that is, again, we'll draw like a line directly in the middle, or as close to the middle as I can. A ray of light that's parallel to the principal axis is going to refract as if it originated from, this time around, a virtual focal point. Rule 2. An instant ray that passes through, or is headed for, the virtual or real focal point will refract parallel to the principal axis. Okay, so let's look at this. So we have our converging or convex lens. So this one tells me an instant ray that passes first through the virtual focal point will refract in a direction that is parallel to the principal axis. Or if we're dealing with a diverging lens, if we have a ray of light that is headed, again, we'll draw that vertical line in the middle, headed for the focal point, is headed for the real focal point, refracts in a direction that is parallel to the principal axis. I find rule 2 is the most difficult one to memorize. It's a little more complicated with the lenses in comparison to the mirrors because you do have the two different focal points. You have like a virtual one and you have a real one. As were with the mirrors, we only had a single focal point and a single center of curvature. The good news is that rule 3 is, of all the ray rules we looked at, whether it's in mirrors or lenses, it is the easiest one to draw. This rule tells you that it doesn't matter whether you have a convex or a concave lens. If you have a ray of light that passes through the center of the lens or the optic center, it just does it undeflected. This seems like a really hard fact to believe because how can the ray of light possibly go through a medium without its direction changing? Well, this is why it's important to state that we're dealing with lenses that are very thin. And here's the way I would justify this. Let's look at just the one on the left-hand side, although the right-hand side would have the same justification as well. Let's say at this point, maybe I'll do this in red so we can see it a bit better. Let's say at this point and this point, I wanted to draw tangent lines to represent the slope. Well, those tangent lines would just be vertical lines. Vertical line. If I have two vertical surfaces, what happens to a ray of light when it passes through surfaces that have parallel sides? Well, if I have a ray of light that comes in here, what would happen is it would enter, and then let's just draw a quick normal line. It's going to slow down, which means it's going to bend towards the normal line. So it would come in and then it might like just have a slight deflection. And then when it comes out, it's going to bend away from the normal line. What we know is that's our special case number 1 from the previous lesson, that if we have parallel sides where you go back into the same medium, the instant ray of light is going to be parallel to the refracted ray of light that exits. Now, if we take this medium and we shrink it, so we make it really, really tiny. So let's say the medium is really thin. And then we apply that same rule. Okay, so a ray of light comes in. There's pretty much no distance for this slight change in direction to occur. Like, yeah, it'll be like a really tiny like change in direction, but then right away it's back to being just a ray that points in the same direction. So if we have a thin lens, and we treat like these two sides as being parallel, which the slopes are tangent and parallel, then basically we do have a ray pretty much just go through undeflected. So it's not a bad assumption as long as we assume that our lenses are very, very thin. In terms of mathematical equations, so the quantitative aspect of this, we can actually use the exact same equations we use as for the spherical mirrors. So those equations were the 1 over f equals 1 over di plus 1 over do. We also had hi over ho equals negative di over do. We also had the radius of curvature is half the focal length. And we also had the magnification equation. So the absolute value of my magnification is a ratio of hi over ho to di over do. Sign convention is going to be just slightly different, though. So let's kind of compare this. Let's deal with the focal length. Okay, so focal length for mirrors. For a mirror, it was positive for concave, and it was negative for convex. If you look at the focal length for a lens, the focal length is actually positive for a convex lens and negative for a concave lens. So they switch around a little bit. The reason they do this is because your focal length will always be positive for an optical device that is converging. Your two converging optical devices would be a concave mirror or a convex lens. If you have optical devices that are diverging optical device would be a convex mirror or a concave lens, that gives you a negative focal point. So you kind of like just memorize it, I suppose, just by asking yourself, well, what is a converging device and what's a diverging device? Converging devices are going to have light either reflect towards or refract towards a focal point, and then diverging devices would have light reflect away from or refract away from a focal point. HO and DO, they're always positive. So we'd assume that our objects are erect, so they're pointing right side up, and they're always real. Even though your objects will be on the quote unquote virtual side. So again, the virtual side for a lens would be this side, and the opposite side, because that's where we're forming our images, is the real side. Our object is still a real thing. So because it's a real thing, we do treat DO as a positive number. DI is positive when real. So that means I would form an image on the opposite side of the mirror. And it's negative when it is virtual. So if I form an image on the left-hand side of the mirror, that would be a virtual image. And once again, a real image is something you can project onto a screen and look at. And like using the lens in your eye, it's projecting light onto your retina, which you can treat as a screen. Or a virtual image, I mean, you have to look through the actual lens to see the object. So that could be like using a magnifying glass to look at something. You have to look through the actual magnifying glass to see like the enlarged image. HI is positive when erect, and it's negative when inverted. And you'll see this when you go through the hand and assignment that the same combinations have to occur. Even for a lens, if an image is real, it must be inverted. And if an image is erect, it must be virtual. Okay, so let's get into a couple of examples. I'm not going to go through any mathematical problems. Like I said, the equations are just the same. You just got to be careful with whether the focal length is positive or negative. All right, so I want to sketch and describe the image for the following two diagrams. What I'd recommend doing is, again, we always draw arrays from like the top of the object, which is up here. The first ray I would always draw is the one with the least amount of error involved in it. And that would be the one that is rule number 3, which tells me that if I have a ray of light that passes through the optic center, it just does it undeflected. Again, as long as the lens is thin. I'd say the next easiest one to draw is probably rule number 1, which tells me for a convex lens, if you have a ray of light that is parallel to the principal axis, it is going to refract through the real focal point. Again, this one is the real focal point. I can see down here I have an intersection point between those two rays. And the way you draw the image is from the principal axis to the intersection point. So I can draw an arrow that points downward. And then let's see if we can get the third ray to confirm this. Again, most of the time you can use the third ray to just double check to make sure you got the intersection point correctly. But sometimes you won't be able to draw the third ray. Okay, so the second rule tells you if you have a ray of light that passes through the virtual focal point, then the ray of light refracts parallel to the principal axis. So what do we know about our image here? Well, it's on the side opposite of the lens. That is the real side. Therefore, the image type is real. That means you could actually take that image and project it onto a screen. The orientation is upside down or inverted. And how does the size of the object compare to the image? Well, it's a little bit bigger. It's enlarged. B. So now I have a diverging lens or a concave lens. And once again, I'll start off with the easiest ray. Doesn't matter whether it's a concave or a convex lens. If you have a ray of light that passes through the optic center, it does it undeflected, as long as we make the assumption that it is a thin optical lens. Then I'm going to apply rule number 1, which tells me that for a diverging lens, if you have a ray of light that is parallel to the principal axis, it is going to diverge as if it originates from the virtual focal point. So again, this is the virtual side. I can see the intersection between my two rays. And again, what you're looking for is the intersection between the refracted rays. Again, you can backwards extend them if you need to. So I have an intersection point between those two rays that's at this green dot. And again, the way to draw the image is from the principal axis to the dot, which would be an arrow that points straight up. Let's see if we can get the third ray to intersect this. So the third ray, which is going to be the second rule, tells me that if you head for the real focal point, we draw this side as a dashed line because that ray doesn't actually get to that focal point. It's going to hit the lens and it's going to change direction before it does it. But we're just targeting it. So when that ray of light targets the real focal point, it refracts parallel to the principal axis. At first glance, it doesn't seem like there's a ray that does intersect my green dot. But again, if you don't find that intersection point, take your refracted ray and backwards extend it or pull it behind the lens. And if I do that, it does in fact match up with the green dot. Okay, so what is the type of image? Well, this time around, it's on the left-hand side. So again, things are switched in comparison to a mirror. So that's now the virtual side. The orientation is right side up or erect. And the size in comparison to the object is, well, it's smaller. So it's reduced in size. Well, that's it for this lesson. And you can complete the thin optical lenses hand-in assignment, which is kind of broken into two parts. The first part has you doing some ray diagram sketching and then identifying what kind of image is produced in terms of its size, orientation, and the type of image. And the second part of the assignment deals with mathematical equations. And I will talk to you next time.